Okay. Morning, guys. So, what we will do today is I will just touch base a bit, clarify a bit on PDA, and then we will jump into pumping lemma. Okay. Yeah. So, just give me a second. Let me share. Okay. The solutions for PDA is already made available on My Times. So, if you look at, I'm sharing the module site on My Times. You can see tutorial 5 PDA. The answers already here. I already uploaded Thursday after our class. Okay. So I just want to clarify a few things based on the discussion we were having after, towards the end of the class or after the class as well. So this is the PDA. Okay. So this question, let us go to the last one. Okay, let's go to the last one. Question number 3. Yeah. Question number 3 says construct a PDA for the language over A, where if the strings have any B's, then all A's receive all the B's. So the condition is if the string have any B's. So the string need not have any B's because here the specification says the string is made up of the alphabets A or B, any combination. So we can have strings purely A, purely B, or a combination of A and B. So these are the possible strings. So the condition here is if the string has any B, then all A's must appear, precede means appear before all the B's. If there are any B's, if there are no B's, then it means the string is going to have purely A's. If the string has purely A's, then this condition does not apply. So that's what we have given here. We have taken purely A's as example strings. And here, when we have a B, we ensure the A appears before the B. Okay, and the number of A's and B's need not be equal. That is also explained in the class. So here, in this question, the only requirement is we can have purely A. If there are A's and B's, then the A's must appear before all the B's. So the number of A's and B's need not be equal. So we are not going to count the number of A's so that we can produce equal number of B's. So we are not going to count, right? So we just need to ensure the A's are processed before the B's are processed. And that's what I have done here. At Q0, maybe take this example string AB. So at Q0, I'm saying A means push A, right? And then what I'm doing is I am doing a lambda transition. Sorry, I'm sorry. A, B, right? Okay. A means I'm going to use this instruction. So A means I'm going to push A. I will be at Q1 now. So B means I pop the A. I repeat one more time. AB means, so A means I'm using this instruction. A means I push A. B means I pop the A. So stack will also be empty. So entire string has been processed. Machine is at the final state. Halt and accept. Sorry. So what happens when we have 4 times A and 2 times B? So we take this example. So 4 times A, 2 times B. So what I will do is for the first 2 A's, I will use this instruction. A means ignore the stack. Let me pull the stack. So this A means is given as input at Q0. So at Q0, I will use this instruction. So currently the stack is empty, right? So I will ignore the stack. For the first A, I will ignore the stack. Second A also, what I will do is I will use this instruction and I will ignore the stack. So A is still red now. A is red, but we are not pushing or popping anything from the stack. Okay, for the first 2 A's. Why I'm doing this in the sense, if you see, I have 2 A's here now, right? There are 4 A's, right? There are 2 A's now. So my thought process is for these 2 A's, I will push A, and when come to B, I will pop the B. Okay, as I said, we are not going to do any counting here. We just want to ensure the A's are processed before the B's are processed. That's all. So that by doing that, we are ensuring the A's appear before the B. Okay. So first 2 A's, I ignore the stack. When come to the third A, what I will do is I will use this instruction. A means push A. So A will be pushed into the stack. Now fourth A means I will use this instruction. A means push A into the stack. So one more A is pushed into the stack. And now B, yeah. So B means I will use this instruction, pop A. Sorry, pop A. B means pop A. And last B, again I will use this instruction. B means pop A. So the entire string has been processed. Stack is empty. And the machine is also at the final state, halt and accept. Okay. So I've given here clearly the above PDA is one possible answer for the given question. Okay. So there could be other possible answers. Okay. So to me, as I have discussed in class, as far as the machine accepts valid strings and the machine does not accept invalid string, then the machine is correct. Okay. So the machine should accept valid strings and the machine should not accept invalid strings. Okay. So if we can ensure that, then the machine is correct. Okay. So we may have, more than one answer possible. Okay. All right. So this one. So this one has, I've shown 2 answers here. I will also tell you how I arrived at this simple possible solution for this question. Here, this question says, construct a PDA for the language over A or B. Up to here, what it means is the strings are going to be made up of the alphabets A or B. Okay, the strings are going to be made up of the alphabets A or B. Where, so that was a condition. Okay, we understand the strings are made up of the alphabets A or B, but what pattern of strings? So the pattern of strings is going to be where the strings contain the same number of A's and B's. So if there are 1 A, I should have 1 B. If I have 2 A's, I should have 2 number of B's. So the sequence does not matter. Sequence does not matter means A can appear first, B can appear first, the string can end with A, string can end with B. So any combination. Okay, the A and B can be in any combination. Only requirement is the number of A's and B's must be equal. The number of A's and B's must be equal. Okay, so I've given some example strings here. Okay, looking at different possible combination. Okay, so let me pull the stack. As I said, the stack is only for us to understand. Okay, you no need to show the stack in the test or in the exam. Okay, it's just to visualize, how the machine works. So it's very easy to see how the machine works. Okay, so let me take this string ABBA, ABBA. Yeah? So this string ABBA will given as input at Q0. So when we give input at Q0, what will happen? A means I will use this instruction. A means push A. So push A into the stack. So now B. So B means the machine will transit from Q0 to Q1. The machine will transit from Q0 to Q1, and B means it will pop the A. You say read A, write lambda. And at the stack top, we have A, replace it with lambda. So A will be popped off. So now the machine is at Q1. So now we have BA still to be processed. So B means I'm going to use this instruction. B means push A. Sorry, this is pop A, right? Okay. B means push B. So B means push B. So I'm pushing B into the stack. And A means we have an instruction here. A means pop B. That is on the stack top. Currently we have B. Replace it with lambda. So meaning pop the B. Processed. Okay. So this is, I mean, again, this question does not has only two different answers. It depends on how you are constructing the machine. We can have actually more number of solutions. Okay, how we want to construct. But here, I'm sorry. How did I arrive at this single state machine? I've also told you. I've also put a note here. For certain PDAs, it may be possible to construct with a single state. Please don't think always in terms of a single state for every PDA. So what I mean is, for certain questions, we may be able to construct a single state PDA where the start state itself is the final state. Okay. For every PDA, we may not be able to construct a single state PDA. For some PDAs, we need to have minimum 2 states. Some PDAs, minimum, we need to have 3 states. It depends on the problem. Okay. So we cannot apply one solution to fit every problem. Okay. We cannot apply one solution to fit every problem. Okay. It depends on the nature of the problem. Okay. In this case, what prompted me, what prompted me to think of a single state machine is, if you observe carefully, if you let me make it a bit smaller so that you can see the, if you observe carefully, put it up. If you observe carefully, whatever I'm doing here, I'm doing here as well. A means push A, B means push B, correct? Or A means push A, then B means pop A. A means push A, B means pop A, okay? That is already here. A means push A, B means pop A. Then I'm saying B means push B, then A means pop B. B means push B, A means pop B. This instruction is also here. B means push B, A means pop B. So whatever I am doing here, exactly I'm doing here as well. So I no need Q0 because whatever I'm doing here is exactly I am doing at Q1 as well. So these instructions, these 4 instructions are exactly here as well. So I no need this. I can do these instructions here itself. And if you observe, that's what I'm doing here. In the second solution, you are having only this part of the machine. in the second solution, second answer, you have only this part of the machine. You can see here A means push A means push A, B means pop A, B means pop A, B means push B, B means push B, A means pop B, A means pop B. So usually when I construct, I don't constrain my mind in terms of constructing a smallest possible machine. I don't constrain my mind. When I look at the problem, I try to understand the problem, and then just try to arrive at answering it. After solving it, then I think whether I can improvise it with reduced number of instructions or reduced number of states. Okay, because it is not like magic, the solution, unless the solution is known already, we can't say this is the smallest solution. Okay, I mean not smallest solution. Unless we know the solution already, we cannot directly arrive at the smallest solution. Okay, we always say there is always opportunity for improvement. So we arrive at the solution first, we solve the problem first. Okay, without constraining our thought, I need to construct a smallest machine. I just solve the problem, construct the machine first. After constructing, I will check whether my machine works. If my machine works, I'm happy. Then I think whether I can improvise it. Okay, to make it smaller. Smaller maybe in number of states, or a combination of smaller in terms of number of states and the instructions. Okay, that's why I said, so here I thought of doing this machine in a single state because I can do all this in one state. Because whatever I'm doing here, I am doing it here as well. So I can just do it here once. Why should I do it two times? This is the thought process. Okay, yeah. So whatever solution I have given here is, I've given written clearly. It is always one possible solution. Yeah, is one possible solution. So for certain answers, I've given two solutions just for you to see. Okay, you can try as well at home. This one, question number 1C. Yeah, question 1C, which we discussed in class. It says the language is set of strings that are element of A or B Canesta, where the string has twice as many B's as A's. So twice as many B's as A's means the number of B's should be twice the number of A. That's all. So the string can be made up of any combination of A or B. Okay, A can appear first, B can appear first. The string can end with A, end with B, doesn't matter. Okay, so the string can be made up of any combination of A or B. Only requirement is the number of B's should be twice the number of A's. So I have taken three simple strings: ABB, BBA, and BAB. Okay, and if our machine works for accepting these strings, I said it'll accept all pattern of strings, all valid strings, because all valid strings, it will follow this pattern. For example, I may have a string like this: A, BB, BB, A. So if you look at this ABB is nothing but this one, right? And this part of the string is nothing but this one. Okay. So what I'm trying to say is, usually it will be made up of a combination of these strings. Okay, so if you look at this string, this part is BAB, right? BAB is here, and this part BBA, this part BBA is here. So usually the strings in here will be made up of these substrings as building blocks. Okay. One exception, that is, one of you in the class, you also had that string and you were discussing after the class, something like this. I remember you had 4 B's and then 4 A's, and again 4 B's. So this string has 2 times B, right? Yeah, you have 8 B's and 4 A's. The number of B's is twice the number of A's. Okay, so for this string, okay, so I also said in the class, we just need one more instruction to tackle to handle this pattern of strings. So that is nothing but this lambda transition. So in the class, I showed you these instruction. I showed you this, and also this, and also this. I explained this. Only instruction I didn't show is this one. So I have included this one, which will now that this answer is complete. Okay, it's not incomplete. Now this answer is complete. It can handle this string. I will show you. Just to recall, I will run this string. I will trace this string, and then I will trace this. Just to recall, before we discuss tracing this instruction, let me pull the stack so that you can visualize how the machine operates. Okay, let's trace this BBA. So BBA will be given as input at Q0. So initially the stack is empty. That's a requirement. Before processing the string, the stack must be empty. So now BBA. So B means we cannot use this instruction because this BBA is given as input at Q0. B means we cannot use this instruction because it says B means pop the A, read A, write lambda. So on the stack, we already have A, but our stack is empty, right? So we cannot apply this instruction. So for BBA, what we do is, what the machine does is, it will use this lambda transition. When the input is nothing, do nothing to the stack and go from Q0 to Q1. Transit from Q0 to Q1. Okay. So now the machine is at Q1. Now we can process this B because we have an instruction here. B means current on top of the stack. Currently it is empty. Replace it with B. So meaning we push B into the stack. The machine pushes B into the stack. Okay. So again B. So again B means so on top of the stack it is empty, right? Because when we want to push something, it can be only pushed on top of the stack. Okay. So top of the stack is empty. So we are pushing, replacing it with B, meaning we are pushing B into the stack. So BB has been processed. So now we have A. The machine is still at Q1. So A means we have an instruction here. A means replace 2B with lambda. So 2B with lambda means this B will be replaced with this B, and this B will be replaced by lambda. So lambda is empty string, meaning we are popping these two B's from the stack. Okay, this is just to recall how this machine works. Now let us recall tracing this string. So BAB. Okay, so again, you see before processing this string, the stack is empty. So BAB will be given as input at Q0. So for this B, we cannot process or use this instruction because this instruction says B means pop A. We cannot pop an A from an empty stack. So what the machine will do is doing nothing, it will transit from Q0 to Q1. Now the machine is at Q1. So B means we can use this instruction. So B means push B into the stack. Okay. So next is next letter is A. A means here it says on the stack we have two B's. Replace it with lambda. But inside the stack we have only one B. So we cannot use this instruction. So what we will do is we will use this instruction. The machine will transit from Q1 to Q0 using this instruction. This instruction says if the input alphabet is A at Q1, okay, read B, write lambda. That is, replace the stack top that has a B with A. Replace the stack top that has a B with A. So here we have B, so it be replaced by A. Okay, so I have told a few times that this position is also called as stack replacement. Okay, so this position is the current stack top and this position is the new stack top. So B has been replaced by A. Okay, so now the machine is at Q0. So now we have a B here. So B means here we have an instruction. Currently on the stack top, we have an A, replace it with lambda. That is read A, write lambda. So this A will be popped off. So this instruction has been processed. Okay. Stack is empty. Machine is at the final state. Alt and accept. Okay. Now let us process this string. Okay. We are going to process this string. Okay. So initially stack is empty. The string will be given as input to Q0. So B means, again, we know that we cannot use this instruction because it says B means read A, write lambda, pop an A from a stack. Stack is empty. How to pop an A from an empty stack? It's not possible. So what we do is we use lambda transition. That is, the machine uses lambda transition and it will transit from Q0 to Q1 doing nothing. Doing nothing means doing nothing to the stack. Okay. So it neither pushes nor pops anything to the stack. It just transit from Q0 to Q1. Now the machine is at Q1. So B means we can use this instruction. Okay. B means we can use this instruction. So what is this instruction? B means push B. Okay. So B means push B. Okay. Again B. So again B means push B. Again B for push B. Again B, push B. The machine is still at Q1. Yeah. So 4 Bs have been pushed into the stack using this instruction. The machine is at Q1. Okay. So now next alphabet or letter is A. So A means here the instruction says pop 2 Bs from the stack. Replace 2 Bs with lambda. That is pop 2 Bs with lambda. So sorry, pop 2 Bs, A means. So this A means these 2 Bs will be popped. Now this A. So this A means again pop 2B from the stack. These 2 Bs have been popped from the stack. If you observe, the machine is still at Q1. Okay, the machine is still at Q1. Okay, so we have processed up to this. Okay, I'll just create a space here just to see where we are. Okay, we have processed this part of the string. Okay, now we still have 2 A's and we still have 4 B's. Okay, so now the machine is at Q1. Okay, so what I'm going to do is I'm going to use this lambda transition. Okay, using this lambda transition, the machine will go from Q1 to Q0. The machine is at Q0 now. So now A means I can process it very easily. I'm going to apply this instruction. A means push 2 A's into the stack. Now this A means again use this instruction, push 2 A's into the stack. Sorry, push 2 A's into the stack. One letter in each cell. Now this B. So B means, so we are going to say pop A, read A, write lambda. So pop A. So again B, machine is still at Q0. B means read A, write lambda, pop A. Again B, pop A. Again B, pop A. So entire string has been processed. Okay, stack is empty. Machine is at Q0, which is also a final state. Alt and accept. Okay, yeah. So what I have added is, after our discussion in the class on Thursday lecture, this instruction. So some of you were discussing, I was telling you, we just need to add one more instruction to handle this. This is the instruction, that's all. Okay, yeah. Okay, this one, okay, we discussed. This one, I will show you, we can improvise it. I just showed this solution. This can be improvised. How means, so here, just to recall, A length I, B length J, C length K. So you see there are no commas separating A, B, C. So meaning A should appear first, followed by B, followed by C. We cannot have any combination of A or B or C. So there is no OR here. There's no comma, so there's no A or B or C. It has to be A, B, C in that order. Okay. But here there is a condition. I is equal to J or J is equal to K. Okay. So I is equal to J means length of A and B are going to be equal. I is equal to J means the number of A and B are going to be equal. Okay. J is equal to K means the number of B's and C's are going to be equal. Okay. So, so now I am visualizing what would be the string, what will be the example strings if I is equal to J. This condition is true. If I is equal to J, I need to ensure only the number of A's and B's are equal. So here I have one time A, one time B. I don't care how many C's are there. Okay. So you can see here one time A, one time B. I can have any number of C's. We don't bother. Okay. We only are concerned about the number of A's and B's. They must be equal. Okay. We ignore the number of C's. Okay. So the thought process is very simple. So A means we push A. That's what I'm doing here. A means we push A. B means we pop the A. When come to C, we simply ignore the stack. You can see here, we simply ignore the stack. So A means push A, B means pop A means what we are doing means, so we are trying to count whether the number of push is equal to the number of pops. If the number of push is equal to number of pops, then the number of A's and B's are equal. So for every A, I push an A, and for every B, I pop an A. So if the push and pop is equal, then definitely the number of A's and B's will be equal. Okay, very simple thought, and that's what what you're seeing now. This part of the machine shows. Okay, the upper part of the machine shows. Okay, okay. So now J is equal to K. J is equal to K means we need to ensure the number of B's and C's are equal. We don't worry about the number of A's. A can be any number. Only the number of B's and C's should be equal, and that's what we are seeing here. So the number of B's and C's are equal. And A can be one time, A can be two times, A can be many times. We don't bother. We only worry about the number of B's and C's. They must be equal. You can see here 3B, 3C, 2B, 2C, 1B, 1C. The number of A varies. Okay. So this part here, the thought process is very simple. So what we do, so B means we push B, C means we pop B. You can actually push any alphabet you want. B means not necessarily you have to push B. You can even push A. You can push C, D, E, F, G up to Z. Whichever capital letter you want, you can push and pop. Okay. I to make my thinking simple. I just think A means push A, B means push B. I think like that. Okay. So that I don't mess my thought. I don't mess up my thought with thinking differently. Okay. Yeah. So that's what you are seeing at the second part of the machine. Okay, so you can see A means we are ignoring the stack because we don't worry about the number of A's. We only worry about the number of B's and C's. So you can see here B means I'm pushing B, B means I'm pushing B, C means I'm popping B, and C means I'm popping B. So here again, if the push and pop are equal, then the number of B's and C's are equal. Actually, we can simplify this. I will show you. I just copy this machine. Okay. I just copy pasted the entire answer here. Okay, and I'm going to show you how we can simplify. Okay, actually now this machine has 1, 2, 3, 4, 5, 6 states, right? So what I can do is I'm saying here A means ignore the stack. A means ignore the stack. Why I'm doing like this means I can have many A's, right? You can see we can have many A's. So A's means we ignore, we don't do anything. Only B means we push something, and C means whatever we pushed, we popped off. Okay. So we are going to ignore the stack. when it is purely A for the second part of the question. Okay. So I'm doing that here. I'm doing that here. What I can do is I can do that anyway. This instruction is going to work at Q0. Correct, right? I can just push it here. It's Vedant. I'm thinking. I think. I think this cannot simplify this. If I put it here, this could accept invalid string. So I was thinking. I was thinking like this. It looks simplified, right? Yeah. Let me bring the stack and show you. This is one thought, but I can see it will accept invalid string. So like, we cannot simplify. I will show you. Don't worry. See, there is no shortcut here. Shortcut here means what I mean is only by practice you learn. Okay. There's no shortcut to learn fast. Okay, let us not go there. Yeah. So let me take this string. I put it here. So A means we are going to use this instruction. Ignore the stack. So you may ask how the machine will know this A means it has to use this instruction and not use this instruction, because this instruction is also for input alphabet A. This instruction is also for input alphabet A. So I've told you in the class, the machine doesn't know. Okay, the machine will not know which particular instruction to follow when there is a choice. Okay, here there is a choice, correct? So A means it can use this instruction or this instruction. So for this string, if the machine uses this instruction, it won't work. Okay, it has to use this instruction and take this path, Q0, Q3, Q5. It has to take this path, only then it will work. Okay, so how the machine can determine that, find out that? It cannot determine that. That's why we call it as non-deterministic. Okay, so PDAs are by nature non-deterministic. Okay, for certain PDAs, we can convert non-deterministic PDA to a deterministic PDA, like we do in NFA DFA. In NFA DFA, for every NFA, a DFA is possible. Okay, for every NFA, a DFA is possible. But the PDA, for every non-deterministic PDA, is there a deterministic PDA possible? No. Certain non-deterministic PDA can be converted to deterministic PDA, but not all. And that's why we say PDAs are by nature non-deterministic. Okay. So let me trace this, and somebody has a question. I'll finish this and come back to take this question. Okay. Okay, I can take this question. This question says, Praptan Diswana, we don't need that lambda anymore, I believe, since we already have a loop of it in Q0. Yes, you are correct. This one is not necessary because we already have it here. So I put it here. What will happen is this, even my earlier answer will accept invalid string. Okay, I will show you, don't worry. Let me process this instruction, and then I will show you that this answer will also accept invalid strings. Okay. So for how many A's? 5 A's, 2B, 2C. Yeah. Okay. First A, the machine will use this instruction, ignore the stack. Second A also, the machine will use this instruction, ignore the stack. So it will do the same for all the 5 A's. All 5 A's, it will process this instruction, ignoring the stack. Okay. So now B here. So B means the machine will transit from Q0 to Q3. Okay. Because here this instruction means B means pop A. We cannot pop an empty A from an empty stack. So the machine will process this instruction. B means it will push B into the stack. Again B, right? So we have the instruction here. So B means push B into the stack. So now C. C means the machine will transit from Q3 to Q5. It will pop this B. Because here C means it says read B, write lambda, pop B. So we have one more C. The machine is at Q5. C means read B, write lambda. So this B also will be popped off. So it works, correct, right? It will also work for invalid string. I will remove this. BBCC. BBCC is an invalid string. Why means some of you might think the number of B's and C's are equal, and we say that we don't care about the number of A's when J is equal to K. When J is equal to K, we say we need to ensure the number of B's and C's are equal. We don't care about the number of A's. But yes, true, we don't care about the number of A's, but we cannot have 0 A's. Why means you look at the condition for the loop variables. I, J, K must be greater than 0. Okay, so this string BBCC is possible only when I is equal to 0. When I is equal to 0, this part of the string will not be there because A will be repeated 0 times. You will get only B and C. So this is an invalid string. We need to have at least one A. We don't care about the number of A's, but we cannot have 0 A. Minimum there should be 1 A. Okay, so this string will be accepted by this machine. I will show you. B, right? So B means the machine will process this instruction. B means push B. So again, we have a B. So it will use this instruction. So B means push B. Now we have C. C means the machine will process this instruction, transit from Q3 to Q5. So this B will be popped off. Again, C means the machine will pop this B as well. Enter string has been processed, stack is empty, machine is at the final state. So invalid string also can be accepted. Okay, so I thought I can simplify this, but cannot be simplified. If we simplify, only way we can simplify is this, and it will accept invalid strings. Okay, so I will remove this. So what is given here is the correct answer. What is given here is already the correct answer. I remove this. Okay. There was a question in the chat. Let me take that. Mohammed Abdi Ibrahim. So how can I know how many states will I need to process the instruction? We cannot find out upfront. Upfront means before solving the problem, by seeing the question, okay, I need to have at least 2 states, 3 states. We cannot decide like that. We just construct to solve the problem and then we see how many states are there. Yeah. Okay. Yeah. So usually when we start, we start with at least 2 states. Okay. If we can finish it within 2 states, we finish it. If we need more states, we try to draw more states. Okay. Yeah. And that's what happens here. The question that we just solved. We started here. When I started answering this question, I started at Q0. I did Q1 and I said we will go in this direction to address this part of the problem. So I didn't think upfront, right? I need to have 3 states. Okay. So I just tried to process these strings. I ended up with 3 states. When coming here, I just want to process these strings. So I ended up with this many states. I did not prefix my mind. So this means I need to have 3 states or 4 states at the bottom part of the machine. No. Okay. Yeah. That's why we say if you look at the questions, it will always say construct. Construct cannot happen in one step. Okay, even building, construction, whatever we construct, it happens, step by step or layer by layer, over time. Okay? That's why philosophically we say, Rome was not built in one day. Yeah, I mean philosophically we say, but any construction has to be done in phases. We just don't do it like that in one go, like that. No. Yeah. So all right, that is about PDA. Yeah. So any questions you all have with the PDA before we go into pumping lemma? Only 39 students are here out of one. I think your class now has come down from 178 to 177, if I'm not mistaken. There are 177 students, but today there are only 39 students. And then later they will say, no, I don't understand this, I don't understand that. Never mind. Students are students. Let us not go there. Okay. So any questions before we go to pumping lemma? Any questions on PDA? Please feel free to ask me. I'm here to help you. I can clarify before we move on to pumping lemma. How do we, I'm looking at Hazik's question in chat. How do you process string AAA for question 3? AAA for question 3. Okay, let me switch to question 3. Question 3. Question 3. 2, 3. Okay, very good question. Question 3. Let me pull the stack so that you can visualize. Construct a PDA for the language over A or B, where if the strings have any B's, then all A's precede all the B's. Okay, so we can have purely A's. So Hazik question is how the machine will process 3 A's. So let me have 3 A's here. 1, 2, 3. Okay. So first A, the machine will use this instruction because this string AAA will be given as input to Q0. So first A will be processed here at Q0. So A means it says lambda stroke lambda, meaning don't do anything to the stack. Read A, the machine reads A, read A, ignore the stack because lambda stroke lambda, right? Ignore this thing. Okay. The machine is where? Still at Q0. So now second A, right? The second A also can be processed at Q0 itself. Again, A means ignore this thing. Ignore this thing. Third A. For the third A, the machine will transit from Q0 to Q1. Again, ignore the stack. Machine is at final state. Stack is empty. Alternate sum. So some of you may ask, how do the machine knows for the first 2A to process this instruction at Q0, and for the third A, it should not use this and use this. The machine does not know. That's why we say it is non-deterministic. If the machine processes all this 3A at Q0, first A means read A, ignore stack. Second A, read A, ignore stack. For the third A, again read A, ignore stack. It uses this instruction. The machine will halt at Q0. If the machine halts at Q0, it is halt and reject. Okay, but AAA is a valid string. Okay, what theory says is this is not only for PDA, also for NFA. Okay, so for NFA or a PDA, for a valid string, there may be many path, many route in the machine. Okay, certain route or certain path will work. Certain path or route will not work. Okay, that's what is here. If all the 3A's are processed at Q0, it doesn't works. Doesn't works means it will be halt and reject, but string is a valid string. For the third A, the machine must transit from Q0 to Q1. Okay, so what theory says is, as far as there is at least one valid path that lead to success, the machine is correct. Okay, that's why we say these as non-deterministic. The machine by itself cannot determine, right, which path to follow that will lead to success for a valid string. It is non-deterministic. Okay. Yeah. What are the differences, Mohammed Abdi Ibrahim? What are the differences between A, comma B, AB Clanesta, A, comma B Clanesta, also A Clanesta, B Clanesta? Oh my God, this is a very fundamental question. Okay, anyway, good that you asked. Let me copy these. Okay, so Mohammed Abdi is asking what are the differences between these strings. So AB means is just AB, that's all. Okay, they are not repeated. Okay, yeah. To me, AB or A comma B, these two does not make anything. That does not mean anything. Okay, yeah, I'll remove it. Here, this yes. AB Clanesta, this I can explain. I will explain one by one. AB Clanesta means there is no comma separating A and B. Here, A or B Clanesta. So this and this are different. Okay, so what this means is AB is seen together because you have a bracket. Okay, and there is no comma separating A or B. I mean A and B. Sorry, there is no comma separating A and B. So they are seen together. So A and B is together. So you should see AB together as one letter. Okay. So now it says AB Clanesta. So this means AB can be repeated 0 to infinite time. Clanesta can take a value 0 to infinity. Minimum value Clanesta can take is 0. Maximum value Clanesta can take is infinity. Okay, so if Clanesta takes a value 0, it means this AB is repeated 0 times. So 0 times means it will be empty string. So you will get lambda. Okay, you will get empty string because Clanesta equal to 0. This Clanesta means iteration or repetition or length. So length means how many times this AB can be repeated. Okay, so Kleiner star 0 means AB can be repeated 0 times. It means the string is empty. So lambda. If Kleiner star is 1, AB together is repeated 1 times. So AB. If Kleiner star is 2, AB can be repeated 2 times. AB, AB. If Kleiner star is 3, AB can be repeated 3 times. Okay, I just put etc. and so on. Okay, so now A comma B Kleiner star. A comma B Kleiner star means the difference between this and this is the A and B here are separated by a comma. So when separated by a comma, we read this as A or B, or apple or banana, coffee or tea, that or A or B Kleiner star. So A or B Kleiner star means it does not means A is repeated Kleiner star times or B is repeated Kleiner star times. No, it is not like that. A or B Kleiner star means the string is made up of the alphabets A or B. Okay, the string can be made up of the alphabets A or B, any combination. Okay, any combination. Then what is the length of the string? The length of the string is defined by Kleiner star. So if Kleiner star takes a value 0, it means A or B, the string made up of A or B is repeated 0 times. Okay, the string made up of the alphabets A or B is repeated 0 times, meaning it is an empty string. Okay, now when Kleiner star is 1, the string is made up of the alphabets A or B, but the length of the string is only 1 character. When Kleiner star is 1. So I can have A or I can have B. The string can be simply A or the string can be simply B because Kleiner star is 1. So Kleiner star 1 means it means the string is going to be made up of 1 character only. Okay. So now Kleiner star is 2. 2 means the string is made up of the alphabets A or B whose length is of 2 characters. Okay, the string can be of 2 characters. So we can have a string purely made up of A. We can have a string purely made up of B. We can have a string made up of both A and B. Not necessarily A should appear first. B also can appear first. So we can have BA also. So when Kleiner star is 2, we can have AA, we can have BB, we can have AB, we can have BA. Okay, I put etc. It grows like this. When Kleiner star is 3, you can have triple A, you can have triple B, you can have AAB, you can have ABA, you can have ABB, you can have BAA, you can have BAB, you can have BBA, etc. It grows like that. Okay, so now this doesn't, okay, this one, A Kleiner star, B Kleiner star means when both the Kleiner star takes a value 0, you get again empty string. When both the Kleiner star takes a value 0. Okay, but when this Kleiner star takes a value 0, this Kleiner star also need not take the value 0. Meaning these two Kleiner star can take values independently. Okay, they need not take the same values at the same time. They can take different values. Okay, but I'm taking the minimum possibility. When both the Kleiner stars are 0, it means A is repeated 0 times, followed by B is also repeated 0 times. So meaning you'll get lambda. Okay, so you can have a scenario when this Kleiner star is 0, this Kleiner star alone can take some value. So when this is 0, what happens? This Kleiner star takes a value 1. You will get B. Okay, when this is 0, what happens? This Kleiner star takes a value 1. You will get sorry, A alone. Okay. So what happens when this also takes 1, this also takes 1? You will get AB. What happens? This Kleiner star takes a value 1, this Kleiner star takes a value 2. So A, B, B. This takes a value 3, this takes a value 2. Then we will have triple A, B, B. Okay, so since this A Kleiner star and B Kleiner star, in between them, they don't have any comma. the A's must be followed by B's. A should appear first, then only B should appear. So A is repeated Kleene star times, followed by B repeated Kleene star times. That is the pattern of string. Okay. So here A Kleene star, comma B Kleene star means these are actually A repeated Kleene star times, comma means is separate. B repeated Kleene star times. You don't have a bracket. Even you don't have a bracket doesn't make any difference. Okay. Yeah. So this means you can have A Kleene star means you can have lambda. B also you can have lambda. Right. Actually, no point saying like this. It should be like this. So A one time, Kleene star takes a value 1, you will have A one time. If Kleene star takes a value 2, you will have A two times. If Kleene star takes a value 3, you will have A three times, etc. Same goes here. When B Kleene star takes a value 0, you will get Kleene lambda empty string. If Kleene star takes a value 1, you will have B one time. Kleene star takes a value 2, B two times, 3 times, etc. This is how it goes. Understood, Mohammed Abdi Ibrahim? Yeah. Any other question before we jump to pumping lemma? Yeah, you're welcome. No worries. Yeah. Good that you all clarify your doubts. Yeah. Okay. So I presume your silence to be you all have no more questions, no further questions on PDA. So I jump to pumping lemma. Yeah. Let me jump to pumping lemma. Just give me a second. Huh? Okay. When we went to PDA, I explained why we go for PDA. That should be in lecture. PDA introduction. Just give me a second. Let me have some water. Okay. Um, I discussed this in class, discussing with you all why we go for a PDA. So we have here this language A lengthen, B lengthen, where n is greater than or equal to 0 is not regular. Okay. So why we say it is not regular? Because we cannot write this language in terms of a regular expression, nor we can represent this in terms of a NFA or a DFA. Okay, we cannot represent this in terms of a NFA and DFA. Okay, so why so? Because n is unbounded. Okay, because n is infinity, right? N is greater than or equal to 0. So A can be repeated infinite times, B can be repeated infinite times. Okay, so the value of n in both the cases, it is unbounded, unlimited. Okay, so here this language means if A is repeated n times, B also should be repeated n times. So if A is repeated 4 times, B also should be repeated 4 times. Okay, so we need to count the number of A's so that we can produce equal number of B's. This cannot be done with an NFA or a DFA because it has limited memory. Okay, so usually we try to decide whether a language is regular or not based on this unboundedness. Okay, n takes a value that is unbounded, unlimited. Okay, which cannot be done with NFA DFA, and that's why we go for a PDA. Okay, so PDA we introduce stack as the memory. But here NFA DFA has limited memory, so we cannot process regular languages. So to process regular languages, we go for PDA. In PDA, we use stack as the memory. Okay, so this is here in my times as PDA introduction. This is not for exam, just for understanding why we go for PDA. Similarly, why we go for pumping lemma. So we can find whether a language is regular or not. It is here. Let me open the slide. Yeah, you can see here, this here. A language is regular if it can be represented as a regular expression, an NFA or a DFA. Okay. A language is regular if it can be represented as a regular expression, an NFA or a DFA. Okay. But what we said just now, we decide that the language is not regular based on unboundedness, right? Unboundedness means limit, the value of n is unlimited. Okay. But what happens is in reality is, let me share this one. This one, pumping lemma preliminaries. What I'm discussing is also there in your my times. It is here. You can see here, this here. Pumping lemma preliminaries. Preliminaries means this also is only for your understanding, not for exam. Pumping lemma is there for exam, but why we go for pumping lemma, like why we go for PDA, right? Why we go for pumping lemma is not for exam, it's just for your understanding. Okay, solving problems using pumping lemma, we will do it shortly. But I'm just introducing you all why we go for pumping lemma. Okay, all right. Let me share this screen. The pumping lemma preliminaries. Just give me a second. Okay. Now, if you look at this language, language, yeah, I'm just giving number. Language 1 is equal to set of strings that are element of A, B, length and A, where n is greater than or equal to 0. Okay. Here we have n. Here also n can take a value maximum infinity. minimum 0, maximum infinity. So here also n is unbounded, right? So even though n is unbounded here, but this language is regular. Usually we say if there is unboundedness, then that language is not regular. But here n is unbounded, but the language is regular. Okay, why? Because this language can be represented as a regular expression. You can see here a, b, canesta, a. I can represent this language as a regular expression, and I can also represent this language in terms of a NFA or a DFA. I have shown an NFA here. A, B, A. This is an NFA. We can even convert this into a DFA. If we can do an NFA, definitely we can do a DFA as well. Tandy, I'm answering Tandy's question. Anything that requires a memory, remembering something is not a regular language, just cannot be present in a regular expression. In general, there are exceptions. That's what I'm discussing in terms of pumping lemma preliminaries. Okay, there are exceptions. You will see now. Yeah, in general, yes, but there are exceptions. So now you can see here. This one we already discussed when we went for PDA. Set of strings that element of 0 length n, 1 length n, where n is greater than or equal to 0. Just now we saw, and the PDA preliminaries. Okay, it's not regular because we need to count the number of zeros so that we can produce the same number of ones. Okay. Again, is all are similar. You see 0 length n, 1 length n. Here it is 0 or 1 clenesta. 0 or 1 clenesta means the I have a condition here. Set of strings an element of 0 or 1 clenesta where the string has equal number of zeros and ones. Something like what we did in the tutorial, A or B clenesta, where the number of A's and B's are equal. So here, instead of A's and B's, you are having 0 or 1. So the language is set of strings that are element of 0 or 1 clenesta, where the string has equal number of zeros and ones. This language is not regular. Why means, again, we need to count the number of zeros so that we can produce same number of ones. Only thing is, the zeros and ones they are not in sequence. They can be in any order. Okay. Yeah. So this language is also not regular. Okay. Now you see this one, set of strings that are element of 0 or 1 clenesta is this question is very similar to this, where the string has equal number of 0, 1 and 1, 0. Here it says equal number of zeros and ones. Here it says equal number of 0, 1 and 1, 0. This language is surprisingly regular. Okay. Though the number of 0 and 1 and 1, 0 is unbounded. Okay. Actually, you implement this with an NFA DFA, you can very easily implement, Yeah. Very easily you can implement this with the help of NFA DFA. Okay. So you see that there are, that's why I said there are exceptions. You see, surprisingly, there are surprises. Even though the number of 0 and 1, 0 is unbounded, right? This language is regular because we can construct an NFA or a DFA for this. Okay. So, so why this situation arises means there must be a loop somewhere in the machine. Okay. And that's why here also, if you see, there is unboundedness, but there is a loop here. The loop is here. The B is looped here. So we call this as pigeonhole principle. Pigeonhole principle means, for example, there are 5 pigeonholes. Okay. And in the morning, all the 5 pigeons go. Evening, when they come back, so they return back as 7 pigeons, but there are only 5 pigeonholes. So the understanding is one of the pigeonhole has to accommodate more than 1 pigeon. We call this as pigeonhole principle. So we try to relate to this principle when there is a loop. So here, so if we have more number of B's, you see, for ABA, we have 3 states. A can be processed here, B is processed here, A is processed here. When we have more Bs, the Bs are processed at Q1. So there is a loop at Q1. Okay. So what the message is, merely looking at unboundedness, we cannot conclude that that a language is not regular. Okay. I've given here all the given examples L1 to L4 require unbounded memory. Language 1 to language 4. That's what I mean. Language example 1 to language example 4. Yeah, I've given four different languages as example. Okay, L1, L2, L3, L4. All these four languages require unbounded memory. However, language 1 and language 4 are regular, while language 2 and language 3 are not regular. Just because the language appears to require unbounded memory, it cannot be classified as not regular. So our intuition means our thought on whether a language is regular or not cannot be merely determined based on unboundedness in terms of memory. So mathematical proofs for certainty means to make sure, to ensure. Mathematical proof to ensure in terms of a language is regular or not regular is needed. And that is where the pumping lemma or pumping theorem comes to help. So pumping lemmas is used to prove that certain languages are not regular. Pumping lemma is just a mathematical theorem. I'm going to explain that shortly. Okay, using which we can prove whether prove a language is not regular. Okay, so when we prove that a language is when we disprove when the language is not regular, it means the language is regular. So a pumping lemma is used to prove that a language is not regular. Okay. So in other words, we can say in simple terms, we can use pumping lemma, which is a mathematical proof, using which we can find out whether a language is regular or not. Okay, using pumping lemma, we can find out whether a language is regular or not. But usually pumping lemma is used to prove a language is not regular. Okay, so let me explain the theorem. Theorem, you don't need to memorize or write the theorem and all that. It's a very simple theorem. I'm going to explain, and then we will take one or two problems, solve it. Remaining problems, we will solve it during our tutorial class. Okay. All right. So let me go to the theorem. Okay. So we are in tutorial 4 now, pumping lemma. Okay. The theorem is here. Maybe I will highlight it in blue. No, I mean, no need to hurry read this. We will come to this later. This is actually the example problem. So what pumping lemma says is, so what this means is we read this as a length. Actually, in mathematics, we read it as modulus of W, right? But here we read it as the length of the string. Okay, the mod is read as length here. These two vertical bars is to mean length of W. W represents string. So the length of, if length of the string is greater than or equal to n, length of the string is greater than or equal to n means I will show you an example here. So let's take this language A lengthen, B lengthen. If n is 1, what will be the example string? We will have AB. Okay. So when we have AB, when n is equal to 1, when n is equal to 1 for this language, n is equal to 1, then we will have the string as AB. Correct, right? AB. So what is the length of the string now? 2. Okay. So length of the string is 2 and 2 is greater than n. So length of the string is actually greater than n. So what the theorem says is if the length of the string is greater than n or equal to n. Okay. So in this case, we cannot have it as equal to n. We will be greater than n in this case, in this language. Okay. So the theorem says if the length of the string is greater than or equal to n, where n is the number of states or pumping length, then we can represent the language as xy length I z, where I is greater than or equal to 0, such that length of xy is less than or equal to n, and length of y is greater than 0. So I will explain what this two line says. If the length of the string is greater than n, greater than or equal to n, something like this, okay, then we can represent this language in terms of xy length I z. We can represent this language as xyz. Okay, I will explain, not to worry, as xyz. Okay. So meaning we can write this language as xyz, where the length of xy must be less than or equal to n, and the length of y must be greater than 0. After doing this, if we pump y, okay, and the resultant string, if it is in the language, then the language is regular. I know you may not understand anything. Let me explain taking this example problem, then you will understand what this theorem says. Okay. Let me do this. Show that the language, show or prove, we can say either way, prove that the language L is equal to A lengthen, B lengthen, where n is greater than or equal to 0 is not regular, using the pumping lemma. We know that this language is not regular because this is the example we took when we went for PDA. We said we cannot represent this language in terms of an NFA or DFA because we need to count the number of A's to produce the same number of B's. We need memory, to say in simple terms. So memory is very limited in NFA DFA. That's why we went for PDA, where we use stack as the memory, right? So we know it is not regular, but we are saying prove that it is not regular using pumping lemma. Okay. So what we are going to do is the theorem already says that if the length of the string is greater than n, okay, we can write this language in terms of xyz. Okay, that is, we can split this language in terms of xyz, where the length of xy must be less than or equal to n, and length of y must be greater than 0. Okay, so I'm going to explain this part, how we can write this language in terms of xyz. Okay, so what I do is the very first step I write like this: let the string is equal to, I'm taking this, let the string is equal to A lengthen, B lengthen, which is equal to xyz, where I is greater than or equal to 0, is an element of L, is regular. So what I'm saying is the string that are produced by this language can be written in terms of xyz. Okay, and I am assuming that this language is regular. Okay, that is, all strings produced by this language will be regular. Okay, so now I'm applying the theorem. If the theorem says if the length of the string is greater than or equal to n, definitely here the string is going to be greater than n. I showed you just now, right? So I can split it in terms of xyz. Okay, so when I split this language in terms of xyz, okay, I have to split applying these two conditions. These are the two lemmas actually. Lemma means theorem. So these are the two conditions. So the length of, I should split this language in terms of x, y, z such that these two conditions are satisfied. That is, length of xy must be less than or equal to n, and length of y must be greater than 0. Okay. Length of xy should be less than or equal to n, and length of y must be greater than 0. Okay. So let me explain this. We are going to write the language a lengthen, b lengthen equal to x, y, z. We are going to write this language a lengthen, b lengthen as equal to x, y, z. Okay. Meaning, when I say a lengthen, b lengthen is equal to x, y, z, I need to say what is the value of x, what is the value of y, what is the value of z. Okay. In layman terms, if I say xy is equal to 4 apples, I take the apples as a. I say xy is equal to 4 apples. The question that comes is x is equal to how many apples, and y is equal to how many apples. Okay. So we can actually take x to be 0. When x is 0 apples, then y will have all the 4 apples. When x is equal to 1 apple, y will have 3 apples. Correct, right? 1 plus 3 is 4. When x is equal to 2 apples, y can be 2 apples. And when x is 3 apples, y can be 1 apple. So xy is equal to 4 apple means, so what is the value x and y can take? So we are splitting these 4 apples between x and y. Okay, this is a very simple layman example. Okay, so this is a natural way of splitting x and y when x and y is equal to 4a's. But here we are going to do the splitting, right? But the splitting is not going to be between x and y, but the splitting is going to be between x, y, and z. So like we said here, we have to say what values x will take. So here I split all 4 apples between x and y, but here it's not 4 apples, it is a lengthen, b lengthen. This a lengthen, b lengthen, which actually represents a string, is going to be split between x, y, and z. So we have to say what values x will take, what values y will take, what values z will take. So when we do the splitting, we have to apply these two conditions. We cannot simply split. What are the two conditions? Length of xy must be less than or equal to n, and length of y must be greater than 0. So we need to apply these two conditions when we do the splitting. So I'm going to show that now. Let me put that condition here. So this is actually the lemma. Using this lemma, we have to do the splitting. Okay, the pumping comes after this. Okay, pumping comes after the splitting. Okay, so I remove this. So now I have to say what values x can take, what values y can take, and what values z can take. We have to find out the values for x, y, z by splitting a lengthen, b lengthen in terms of x, y, z. Okay. You have to observe me carefully. It will be a bit tricky, but once you understand, you can. It's just a cakewalk, very easy. But the initial understanding takes a bit of time. It will be a bit confusing, but once you understand, it's very easy, very interesting. Yeah. So now, okay, we are going to split like this, right? Here the condition says length of xy should be less than or equal to n. That is how I should split x and y. Length of xy should be less than or equal to n. Let's take some value for n. Okay. So what will happen for this language if n is equal to 2? If n is equal to 2, then a lengthen, b lengthen will be equal to what? A lengthen, b lengthen will be equal to AABB, right? Yeah, AABB. Okay. So we are going to split AABB. Maybe I'll take 3 so that the string looks a bit bigger. You can see visualize the splitting very clearly. If n equal to 3, then A lengthen, B lengthen, triple A, triple B. So we are going to split this in terms of x, y, z. Okay. We are going to split triple A, triple B in terms of x, y, z. Okay. So the value of x and y, this is z, sorry. The value of x and y should be such that the length of xy is less than or equal to n. What is n? N is 3. Correct, right? If n is 3, where should be your x and y? Your x and y should be here. Correct, right? Your x and y should be here. Because n says 3. What the condition here says, length of xy should be less than or equal to n. So less than or equal to n means n is 3 means your x and y together should be here. Okay, that's what I've shown here as well. Okay, so x and y should be here. Yeah, x and y should be here. And whatever remains can be thrown to z. Okay, so the 3 a's are going to be split between x and y. Okay, because length of xy should be less than or equal to n. Okay, so your xy is here and your z is here. Okay, so I can throw all the 3 b's to z. Okay, now how we can split the 3 a's between x and y? Okay, like I split the apples, 4 apples between x and y, same thing like that. So I can give, I can assign 1a to x and I can assign 2 a's to y. Okay, so when you combine xy is equal to 3a's, right? And 3a's is same as n, because n we took it as 3. Okay, should be less than or equal to 3. Yeah. So I can take like this. Another option is I can give 2 a's to x and I can give 1a to y. Can I give 3 a's to x and no a's to y? Cannot. Y means here the second condition says length of y must be greater than 0. So y cannot be empty string. Okay. So y cannot be empty string. Length of y must be greater than 0. So I need to have at least 1a with y. So I can have 1a with y, 2a's with x. I can have 2a's with y, 1a with x. I can even have all 3a's with y and 0a's to x, no issue. Okay, x and y together should be less than or equal to n. I have taken n as 3 here. You understand? So we have to split like this. Okay, so that's why I said the xy is here because it has to be less than n. N is 3. Okay, some of you may ask, sir, n is also here. Can I take the xy here? Cannot, because you see it is x, y, z. This whole thing is x, y, z. So if you take the xy here, then z is what? You are actually ignoring this part. You are taking your xy here. Because you might say this n is also for b. So why you are taking only for a? So if you are splitting the b's between x and y, z actually is lost. Because this part you are taking as xy. So z is lost. You can't go and assign z as AAA, cannot. Okay. This whole string, whole language is taken as X, Y, Z. So X should followed by Y should be followed by Z. Okay, that's the sequence. We can't change the sequence. Okay, that's why I said your XY is here. We are splitting the three A's among X and Y. So this is with respect to this example. Okay, this example. So meaning how I can write it in general. Okay, I should write it in general because I just took an example. N as 3. N can be 3, N can be 4, N can be 5, N can be 6, N can be infinity. Because here it says N is greater than or equal to 0. N is greater than or equal to 0, right? So N can take any value. So I cannot simply take some example and split like this. I have to split in general. So what I'm going to do is, so where is your XY here? The A's are going to be shared by XY, right? So meaning your XY is here. I'm sorry. Your XY is here. And your Z is here. So in the language, Z is here. So A length N is going to be shared by X and Y. So what Y should take? Y cannot be 0, right? Y cannot be 0. It has to be greater than 0. So I will take Y as A power K. I take it as A power K, and I'm going to tell what values K can take. What values K can take? K should take a value at least 1, right? Because if K takes a value 0, then A length 0 means Y will become empty again. Y cannot be an empty string, right? So K can take a value, has to take a minimum value 1. So I'm going to say K should take a value greater than 0. K is greater than 0 and less than or equal to N. Less than or equal to N. So in our case, N is 3, yeah? Yeah. So K can be equal to 3, K can be equal to 2, K can be equal to 1. Okay, yeah. But K cannot be equal to 0, right? So if I take Y as A power K, what will be your X? X will be A power N minus K. N minus K. Why N minus K means if K is 1, so N is, for example, we have taken 3. So 3 minus 1 will be 2. So A here 2 times, A here 1 time. If K is 2, then 3 minus 2 is 1. So A will be 1 time here, A will be 2 times here. If K is 3, because I've said K is less than or equal to N. So maximum value K can take in our example is 3. So K is 3 means A 3 times. Here 3 minus 3 will be 0. So X can take a value 0. Y can take 3 A's. Whatever remains will be Z. So Z will be simply B power N. Simply B power N. So we have split the language A length N, B length N in terms of X, Y, Z. We have split the language A length N, B length N in terms of X, Y, Z, applying the lemma, the two conditions. So we have split the language in terms of X, Y, Z by applying the lemma, where the lemma is length of X, Y is less than or equal to N and length of Y is greater than 0. We can't simply split in any way we want. We have to split applying these two conditions. Okay. So now we have just looked at lemma. What the pumping theorem says, pumping lemma says. So following the lemma, we have done the splitting. Now what pumping says is, I'm going to show now. Now we say pump Y. Pump Y means I'm just going to say X, Y, Y, Z. X, Y, Y, Z means originally we took the language as X, Y, Z, right? We took this language to be equal to X, Y, Z. So pump Y means you repeat Y one more time. So the same as pumping Y. Pumping Y means to add Y one more time. So we know what is X, what is Y, what is Z, right? Actually here, if you combine X, Y, Z, you will get back your original language. For example, if I just take X, Y, Z, now we have already split X, Y, Z, right? So what is X? A length n minus k. What is Y? A length k. What is Z? B length n. So what is this equal to? This is same as writing n minus k plus k, correct, right? Same as writing a n minus k plus k b length n. So this is same as writing minus k plus k will get cancelled. You will get a length n, b length n. So we split it. Now when we say x, y, z, we get back our original language. Okay, yeah. So our splitting is correct, huh? So now what I'm saying is pumping y. Pumping y means repeating y one more time. We took the language as x, y, z. So now pumping y means I'm going to repeat y alone 2 times. So pumping y 1 time. Pumping means to add y one more time, huh? Yeah. So pumping y. So x is what? We already split it x as this value. Y is a length k. One more time y. That's what we mean by pumping y. So y 2 times, huh? I've done y 2 times. Then what is z? So I need to rewrite this. A length n minus k into a length k into a length k into b length n. So n minus k, a power n minus k, a power k, a power k. This can be written as a power n minus k plus k, again plus k. So now minus k plus k will get cancelled. You will get it as a length n plus k, b length n. Okay. So this is not an element of n. This is not an element of n. Not an element of n means what is our language? Our language is a length n, b length n, right? It's not an element of n. Yes, I put the element symbol and I have stacked it up. I couldn't locate the symbol for not an element of, or we can simply write not an element of. That's what I've given here, not an element of L. Why I'm saying this is not an element of the given language? What is our given language? A length n, B length n. After pumping y 1 time, what is that we are getting? We are getting a length n plus k, b length n. Meaning, what will happen when you have a n plus k, b length n? We already know k has to take minimum value 1, right? If your n is 3 and k is 1, you will get a 4 times, b 3 times. That is not our language. Our language is a length n, b length n, where the length of a and b are equal. Okay. So what the pumping lemma says is, what the pumping theorem says is, now is easy for you to understand. What the pumping theorem says is, for a language, okay, if the length of the string, okay, you give some values for n, if the length of the string is greater than n, then we can split or write the language in terms of x, y, z. We can write or split the language in terms of x, y, z, where the splitting has to be done applying these two conditions. Length of xy must be less than or equal to n, and length of y must be greater than 0. Okay, so applying this condition only, we split or wrote this language in terms of x, y, z. After doing this, we pump y. Okay, we can pump y any number of times. So what the pumping lemma theorem says is, if we pump y one or more time, and if the resultant string, is still in the language, then the language is regular. In our case, we pumped y only one time, and the resultant string, this is the resultant string, is not in the given language, because our resultant string after pumping is a power n plus k, b power n. But our language is a length n, b length n. Here we are getting a length n plus k, b length n, meaning we will have more a's than b here. Okay, we will have more a's than b. Here, our language is equal number of a's followed by b's. Same number of a's and same number of b's, or the number of a's and b's are always equal. Here, the number of a's will be more than the number of b's. So, the original property of the language is lost after pumping, meaning this language is not regular. So, I repeat one more time. If we can write, okay, when we can write, okay, let me repeat one more time. If the length of the string is greater than or equal to n, then we can write or split the language in terms of x, y, z. Okay, how we do the splitting? Splitting should be such that length of xy is less than or equal to n, length of y is greater than 0. Okay, so following these two conditions, we split the language in terms of x, y, z. After splitting, we pump y. Pump y means add y one more time. We can add y any number of times. Okay, so after pumping y one or more times, if the resultant string is in the language, then the language is regular. If the resultant string is not in the language, then the language is not regular. So here we just pumped y one time. Actually, you can pump y 2 times, 3 times, 4 times, any number of times. Okay, so even after pumping y one time, adding y one more time, if the resultant string is not in the language, then the language is not regular. So we conclude here. Hence, the above language is not regular. And that's what I've done here. I just explained. Okay, exactly. This is what I have done here. I've just explained it here. Okay, any questions before we take one problem and then leave? It's 11:51. You may be hungry. I'm looking at the chat questioner, Shia Ikin. Sir, for derivation, each time we can only derive one variable, or like for lambda, we can do it with the other variable. I don't understand. What do you mean by one variable? What do you mean by one variable or other variable? I'm unable to understand your question. Shia. I'm seeing different questions. Let me first finish Chia first. Then I'll come to Tan and Law Kok Chong. Yeah. Chair question is, if you got SS, can one S be lambda and the other S I do the ABB? What do you where the SS comes from? Yeah. Yeah.
I means like because when we are doing derivation, we got like S maybe equals to AB or S or SS, right? So if we have two S, like two variable, one S is a variable, then can we do both variables at one time? Like derive two variables at one time?
This is for what grammar is it?
No, derivation. The
This
past three.
oh, past three. Oh my. Okay. Because we were discussing pumping lemma, suddenly you asked one variable, two variable, I was lost. You could have told for past three, then I could have understood. That's why I was wondering where from pumping lemma you got lambda, SS, and all that. If you got SS, can one S be lambda and the other S I do the ABB?
Because like we got the rule say like leftmost derivation, right? So like meaning that each time we can only derive one variables or we can derive like two variables, two s at one times.
No. You should expand only one variable at one time. Cannot do two at the same time.
What if one s we put it as lambda, then we also need to derive one at each time, or we can like
you are replacing one S with lambda. So
yeah.
in the next step, you will have only one S. You can do that. Okay, let me show you. So you suddenly jump to past threes. I was a bit lost. Okay, I'm showing you on the screen. You are saying something like this. Correct, right? So you do the derivation, and you want to replace this leftmost S with lambda. Correct, right?
Yes, and then the other s maybe with
Yeah, if
the
you
other thing.
lambda, if you replace with lambda, you will get one S in the next step. In the next step, you can replace this S with whatever rules you have. For example, if you have some rule saying no S is AB, for example, then so you have replaced this S with lambda. So only one S remains. So now you can replace the S with AB and do derivation, no issue.
Can I do like directly SS then ABs?
Sorry, SS?
SS, then the next step I goes to AB.
You go to AB immediately. Like this is it. You cannot, because which yes you have replaced with lambda, we need to see that. So you have to do one step at a time. So in the next step, you have to, if you follow leftmost derivation, you are going to eliminate this s with lambda. So you will have this s left. So you have to say this. Only the next step, you can replace the s with whatever you want. So you should still show only one step. You should do only one step at a time. Okay, yeah?
Okay.
Should do only one
Thank you,
step at a
sir.
time. Yeah, welcome. Okay, let me jump to the next question in the chat. So derivation done. Sir, can you try doing pumping lemma for the question that was deemed as regular language? The one goes 1, 0 clinista, where it has equal number of 0, 1 and 1, 0. I do it. Shia, I do it together. If there is a regular language, it be A length and B length and only, right? If this is a regular language, it should be. Yeah. I've replied the grammar for Tan. Tan's derivation is correct on the grammar. So one step at a time. S is AB or SS means You derive S as SS, then you replace the leftmost S with AB, the S remains, maybe then AB and not SS, AB, AB, correct. Yeah, I put a thumbs up there, correct. So let me roll back. If this is a regular language, it should be A lengthen, B lengthen only, right? I don't understand what is that. I will come back to Tan again on the question 1 or 0. If this is a regular language, it should be A lengthen, B lengthen only, right? What is that question, Kok Chong? You're asking, so if this is a regular language, it should be A lengthen, B lengthen only, right? What is the what are you trying to? I don't understand your question. What do you mean by, so if this is a regular language, it should be A lengthen, B lengthen only, right? I don't understand. What is that? Can you explain your question?
I mean that
Mm.
this answer is no regular language, right? So it become A lambda plus K B lambda. So this is the answer for no regular, right? And if this is a regular language, so the answer should be A lambda B lambda, right? If the answer is A lambda B lambda, it
Oh,
is
okay.
the
After
regular
the
language,
pumping,
right?
after the pumping, right?
Yeah.
Yeah, after the pumping, you should get it as A lengthen, B lengthen. Only then it will be regular.
Oh, okay.
But after pumping, we won't get it as A lengthen, B lengthen.
So if the answer is like this, A lambda plus K B lambda, so it's not regular. But
Yeah, not regular.
if the A lambda B lambda is regular.
Yeah, correct, regular.
Okay, thank you, sir.
Welcome. And now I understood your question. Okay. So now roll back to the earlier question. Try do pumping lemma for the question that was deemed as regular language, the one that goes 1, 0 Clanesta, where it has equal number of 0, 1 and 1, 0. Okay, for this one, first we have to write it as a regular expression. It may be a bit tricky. So it's 12 o'clock. What I'll do is I will show you one example where the language is regular. I'll show you the pumping. Because here, all the questions here, it's already here, right? Yeah. And remove all this. All these languages are not regular. So you don't have a language that is regular here. So what I will do is I will take a language that is regular. I think it's already here. Okay. I will show you this. Okay. So to me, This language is regular. It is also given in the pumping lemma preliminaries. A, B length and A is regular even